Hello, my name is Matthew Brown, and welcome to this lightning talk on preliminary results of the effect of kinetic enhancement on N-heptane droplet cool flames in microgravity conditions. I am a graduate student attending the University of Wyoming, and this work is supported by NASA under the award number seen at the top of this slide. Starting in the top left corner, this study is motivated by previous work which investigated different kinetic enhancement methods that could be used to enhance low-temperature chemistry critical to the stabilization of low-temperature combustion, otherwise known as cool flames. It was found that under premix operating conditions, ozone addition is a more energy-efficient method at enhancing low-temperature chemistry when compared to simply preheating the reactants. This concept can be seen in the figure provided. In this study, we want to explore if the same trends are applicable to cool flames produced via two-stage N-heptane droplet combustion observed aboard the International Space Station, specifically when cool flames are produced via the radiative extinction of droplet hot flames. This is interesting because instead of uniform premix conditions, cool flames are stabilized in a non-premix mode, meaning fuel is diffusing into the flame from the droplet side and the oxidizer is diffusing into the flame from the environment. Now, if we look at the top right corner, a first-step analysis on an N-heptane oxidizer mixture was performed to reveal the effect of each kinetic enhancement method, those being ozone addition and preheating of the reactants, on flame speed as a function of equivalence ratio using one-dimensional cool flame simulations, which were operated at an initial pressure of 0.7 atmospheres. Flame speed is used as a measure of reactivity, and the equivalence ratio is simply the proportion of the actual fuel oxidizer ratio to the stoichiometric fuel oxidizer ratio. So if the equivalence ratio is less than 1, you are burning fuel lean, and if it is greater than 1, you are burning fuel rich. We can see in the figure that the solid lines represent ozone addition and the dashed lines represent preheating of the reactants. We also see that in both cases, the flame speed and thus the reactivity of the mixtures increase with each enhancement method. Furthermore, if we mark the peak flame speed for enhancement with black dots and the red squares appropriately, we can see that ozone addition moves the peak flame speed to linear conditions with increasing ozone enhancement much more rapidly than the preheating enhancement method, which only slightly trends linear. Now, to compare one-dimensional cool flame simulations to droplet combustion cool flames, a droplet combustion model is needed. In this study, OpenSmoke software is utilized to simulate two-stage N-heptane droplet combustion in microgravity. The simulation is validated against experiments performed aboard the International Space Station. The first validation test was performed using a commonly studied initial droplet diameter size of 3.91 millimeters at atmospheric pressure, which can be seen as blue in the bottom left figure. The simulation adequately predicts the time of the hot flame extinction and slightly overpredicts the time of the cool flame prediction when compared to experimental data. A second validation test is performed using a smaller initial diameter of 3.56 millimeters and a lower pressure of 0.7 atmospheres, which matches the one-dimensional simulations and can be seen in red. In this case, the hot flame extinction is accurately predicted, but the simulations overpredict the duration of the cool flame by a significant amount of time. This is concerning and is subject to ongoing inquiry. However, we feel that the simulation has been validated enough for us to begin preliminary inquisitions. Finally, in the bottom right corner of the slide, a figure shows the equivalence ratio of the flame as a function of time for droplet combustion simulations. Due to the non-premix mode of combustion, the equivalence ratio was calculated from the mixture fraction of fuel and oxidizer at the flame. The black line displays a reference case with no ozone enhancement and the environment temperature of 300 Kelvin. Here we see that the cool flame sits at a rich equivalence ratio of 3.45. The blue and red lines display ozone enhancement and environment preheating respectively. For both enhancement cases, equivalent energy was added to the reactants through either the enthalpy of formation of ozone or through the preheating of the surrounding environment. We can see that both enhancement methods cause the flame to move to linear equivalence ratios, but the ozone enhancement method yields a greater change in average cool flame equivalence ratio when compared to the preheating enhancement method. In conclusion, we have shown that both kinetic enhancement methods drive peak low temperature chemistry to linear equivalence ratios, and that ozone does this more effectively than preheating on a unit energy addition basis. We see these phenomena in premix flames and preliminary results for non-premix cool flames during droplet combustion. We are continuing to work to better understand this phenomenon and its implications for droplet evaporation and burning rates. This concludes my lightning talk. Thank you very much.